this is x, sx.
Right.
And all in a z basis, so this is the x-axis there.
That's what I was trying to figure out is.
Yep, no, I screwed up. And then the y one is over here.
So, this bend is the actual stigma of
Yeah.
different ones around. That's what I was trying to figure out.
So,
Okay, so look guys, this shouldn't be, maybe it's my fault, all right? A vector has what components? X, Y, and Z, right? Does this have an X, Y, and Z component? This is Z component, this is X component, this is Y component. Is that like a vector?
Yeah.
Okay, so all I said is that it's a vector of matrices, or a matrix vector. It's all three of those, the X, Y, and Z matrices.
It's just the arrows.
Yes, my arrows are wrong, but this is nothing more than vectors.
Just a quick thing on the operation, which is on the left-hand side. There.
Show my face getting frustrated. Edit that, please.
The operation on the left-hand side of the equation with z, is that like the full vector, or is that the vector? What is that?
The Z basis set.
This is my vector. So I put a vector sign when
Is
it's a
that your
vector.
vector of
It's
all three?
of all three of those. And
So
the
why does it have the z over there?
Because it's in a Z basis. I started out by doing this in a Z basis. You can do this, and and this is something that's not in your book, but later on you can do it in any base. Remember, I can do whatever basis I want that spans 2 dimensions. But I chose this basis set, so I'm just doing it in a Z basis.
Keep that for consistency.
I'm keeping it for consistency, exactly, but the book doesn't do it. The book just leaves it, and then in the back of your head, it's like, oh yeah, I'm doing it in a Z basis later on.
Hmm.
All right? And so I'm saying it explicitly, this is how I built it.
so we built those operators, right? And then if you're saying that the individual S operator is essentially like a vector operator, right? No?
No. Okay, forget the whole vector thing, guys.
No, I like it. I really like
Yeah,
it.
so let's get it, go away.
What happened?
Keep
Gone.
them separated.
All right, gone. We're not going to talk about it. The vectors are screwing everybody up. I have an operator that gives me SZ. I have an operator that gives me SX. And I have an operator that gives me SY. That's what those operators look like. These things alone are called polyspin matrices.
No, I kind of get the other effect. And my question was, when you do it in a Z, are you going to lose out on the X and Y pieces of the vector?
I don't. I say, so the questions I can ask is, what's the expectation of the projection of any momentum in the Z? And I would do that. I would do this. I would look for, this, SZ, this.
So if you're looking at from a different.
That's the expectation value of SZ. I would do that calculation. Then I could ask for the calculation of what is the projection of the X. And I would just use that.
Because the X would have a plus or minus H bar, it would just be somewhere along.
Well, that's what we want to do. So forget about the whole vector part of it. It's really confusing everybody.
So those
I just have an operator that will pull out the projection in the X direction. I have an operator that will pull out the projection in the spinning Y direction. I have an operator that will pull out the projection in the Z direction. That's it.
So those polyspin matrices, each one of those matrices represent a spin in each one of those directions. Is that what they represent?
No, these represent essentially, they're just the matrices by themselves, right? But what they do is when they operate, they pull out the projection in the Z direction, they pull out the projection in the X direction, and they pull out the projection in the Y direction. Okay, guys, I hope to clear out this whole chapter.
But the last
We're not
thing
there.
the Z
So the way the class is going to go, we'll spend the last day finishing the spin. All right, and we're not going to get into chapter 5.
What is the last day?
just the very last
Next
equation with the projection of the Z, the very last thing.
Yeah.
The function that we plug that into, would that be the chi function, or would that be
Yeah, so right here, we'll put in our general chi.
That's all I was asking, that's all I want to know, because
That's it.
we want to make sure that was the right switch and put in there
Yeah.
what my notes.
In, you say the matrices operate on what? When they operate on the language you're using, I just want to get the language down, that's all. When the matrices operate, they give you the projections. What are they operating on? They're operating on,
Okay, so let's give an example. So everybody needs an example. All right? So let's do SZ operator and the Z basis operating on an up cap. What does that equal?
Three-quarters H bar.
So SZ is this one. Let's pull out SZ. It's H bar over 2, 1, 0, 0, 1. What is the
1,
0,
0,
1, 0?
1, 0, negative
negative
one.
one,
equal?
yeah, negative one on the SC operator
No.
matrix, -1.
No, you had, on the first matrix, 1, 0, 0, negative 1.
Yeah. For the Z,
For the poly matrix.
for the
The
Z
three
column
Oh, yeah,
matrix.
yeah, thanks. Gotcha. Okay. What does that equal?
One.
H bar over 2.
It's gonna equal H bar of 2, 1, 0.
So this is SZ times an up. What does that give us? Roll over 2 times an up. So what did SC do?
Give us the projections.
Just pull out in the H bar of 2.
Pulled out the projection of the angular momentum in the Z direction. What does SX do?
Pull out the projection of the X direction.
What does SY do?
Projection of the Y direction.
Okay, so what I did is for notation, I just lumped those together into a vector. All right?
And if you operate those ones on the up, you get a big fat 0.
Say that again?
And those, both SX and SY with an up are going to give you 0.
Yeah, so that's a very good observation. So if I go, so remember, what does that mean? What is an what does this mean? All right, like this gives me the projection of the angular momentum in the Z direction. But what Eric is saying is, what if I did this? What if I calculate the expectation value of X? All right? So now when I'm doing a measurement, I'm calculating, I got to calculate the expectation value. So that equals this. That equals an up, and then SX,
Squeeze the operator.
and then an up. You squeeze the operator in there, and as Eric pointed out, this is going to come up to be
0.
0. So why do you, okay, so first of all, what is an expectation value really? Is it one measurement, or does it represent something
It's
else?
like the average of
So
What's that?
Probability.
it's a probability. Well,
It's the average.
It's the average value.
It's the average, okay?
identity prepared.
So, of identically prepared things. So if you have this situation
So
where the
we're-
spin
The
is
Z
going
basis.
around in a circle like this,
Right.
it's processing around the Z, what is your expectation? What is
X
your
and Y are
average?
both going to be 0.
It's going to be 0. What's going to be your expectation of Y?
0.
What's going to be your expectation of Z though?
H bar over 2.
H bar over 2.
yeah,
Okay.
it's just as likely to be
Yeah.
any X projection.
Okay, good. Yep, gotcha, thank
X
you.
projection. It's
Yeah.
kind of
Okay,
happy.
yep, good.
And
Okay,
that's,
so look, it's not a bad thing. We've slowed down. I truly figured that I'd be done with this, and we're not anywhere close to being done with the spin. All right, and so we will just finish the spin, and maybe I'll outline some stuff about chapter 5 on next Thursday. But we're nowhere close. Yep.
With regards to Tuesday, might it be possible to give like share a couple of problems or like ones to focus on that will be similar to that?
I already talked about that in the beginning of class.
Specific problems?
I'm not going to give you a specific problem, but I'll give you specific. I did say stuff about that at the beginning of class. All right, Matt, did you have a question?
One more call to the second.
It was just about that factor thing. So if we